So we've introduced the idea of an electric field, which tells us something about what happens if we put a point at that spot where X marks the spot. And so we're going to practice with that a little bit more. We're going to say, suppose we want to find the electric field right here at the origin. So we're looking for the electric field at 0, 0. There's no charge there. We don't want a charge there because then R would be 0 and we'd have infinite electric field. That's kind of a problem. And I'm going to say these are 3 identical charges. So Q for each of these is the same, and they're the same distance away. So in all of these instances, they are a distance A away. Okay. So the question is, what is the electric field? Well, before we get going too far, it's useful to take a look at the direction of the electric field for each of these particular charges. So if we look, we're looking at this spot. So I'm going to draw 1 in. So from 1, we imagine a positive charge has just landed in this center part. There's not one here, but the electric field, the force it would feel, would be in this direction. So that's due to 1. Okay, 2 is here, and so it would push a charge in this direction. That would be the electric field due to 2. E2. This is E1, and then for 3, well, 3 is going to go in this direction, E3, and notice that 3 and 1 are going to cancel each other out, which is kind of convenient. So with 3 charges like this, so in this situation, we're going to have a setup. I'll just do this sort of in shorthand. This is just going to be the electric field is going to be here because the outer charges 1 and 3 really don't make a difference. It's just 2 that matters. And that E is going to be equal to K Q over A squared in the minus I hat direction. Okay, I'm going to add some more charges in. So I'm going to add another charge in, let's say right here, and let's say right here, okay? So on equal, they're still a distance A away, okay? And they're at some angle. So let's see what happens here. Okay, so Q2 still points down. 1 and 3 still cancel each other out, so I'm not going to draw them in. But 4 and 5 are interesting. They partially cancel each other out. So 4 takes us along this direction, right? And 5 takes us along this direction, okay? And so 5, this is the angle theta. This is E5. And this is E4. And notice that for E4 and E5, so E4 would be KQ over A squared. That would be the magnitude. And then it would have, in the X direction, it would be cosine theta I hat plus KQ A squared sine theta in the minus J hat direction. Right? That's from E4. That's this vector. Cosine would be like this. Sine would be down. And then for 5, E5, it looks like KQ over A squared cosine theta in the minus I hat plus KQ A squared sine of theta, in the minus J hat. And so if I add these two together, then E4 plus E5 is just going to, these two are going to cancel, and I'm going to get 2KQ over A squared sine of theta in the minus J hat direction. Okay, so those are going to add up in the same direction as my E2. So overall, I would take this plus this to find the sum of all 5 of these. Okay, so you see that this can get fairly complicated. If these were not all the same charge and the same distance away, we wouldn't have a nice symmetry where things can cancel out. But what I want to do is extend this then to a uniformly charged ring. So that's what I'm wanting to do, is to build a ring, actually a semicircle, and ask what is the electric field right in the center. Okay, so that's where we're headed. But what I wanted you to do is see that setting up these vectors actually can save us some work, because in this situation we can tell we're only going to have to worry about a component of the electric field that's down. The x parts are always going to cancel out. Okay, assume this is a semicircle of radius A. It's a little off center, where the y-axis is actually going through the middle of it, and this is the x-axis, and that it is this pink is the charge. This is a semicircular ring of charge plus q, the whole thing. And the first thing we can do is, based on what we saw before, if we're asking to find the electric field again at the origin, which is what we're sort of set up to do, then we know we're going to have an electric field that is only in the negative y hat direction. That's the only direction we have to worry about. Okay, so if we look at some little piece of the charge, say right here, we can look at its contribution, so it would give a little bit of electric field. We can look at only its y contribution. So our program here is going to be find the electric field due to this little tiny bit of q. We're going to call it dq. So we want to find dE from dq. So that would just be dE, the magnitude, is equal to k dq over r. The distance is a squared. That's the magnitude of the electric field. Now we want the y component. Okay, so dEy, if this is theta, if we're measuring it along this direction, so that this would be a theta of 0 and that would be 180, sort of in our normal way of doing things, then we would say that this would be k dq a squared, so this is also theta. So the y component is going to be the one in that direction, so that is opposite our angle, because our angle is here, there's the hypotenuse, that the adjacent is on the green, on the x-axis, so the opposite, so that would be sine of theta. So that's our contribution to the electric field due to that little piece. In other words, it's a little tiny bit there, and then some other piece over here would have some small contribution along that has an x, that has a y component. And we don't have to worry about the x components. And when I write it like this, I hope you can see I'm setting it up to say my electric field in the y direction, which we know points down, is equal to this integral of E dy. I need to add up all these pieces, and that's what an integral does. So this is a weird setup in some ways, because we're setting up the integral from our geometry, which is kind of messy. So we have Ey is equal to this integral k dq over a squared sine of theta. And I'm going to need some limits of integration, right? I want to go from here to here. I want to add up from here to here. I kind of think maybe I go from theta equals 0 degrees to theta equals 180 degrees. Okay, that makes sense. And I can pull some constants out. K is a constant. It's 9 times 10 to the 9th. A is this distance, which is the same for everything. So this becomes K over a squared. Now, this is a messed up integral. I want sine of theta dq. I'm guessing that in calculus class, you usually had like something that looked like an x squared dx, or sine theta d theta, right? You need the variable to match what you're differentiating over. And so far, I don't have these matched up, which is not so nice, right? Particularly when I know I want to keep things in terms of theta. Okay, so how do I do that? So this is the way we do this. We introduce something called a density. We saw this before with gases. We use densities, right? Our mass density would be like rho is equal, this is a mass density, mass per volume. Well, we can do a charge density. So in fact, this I'm going to do a linear charge density, which is going to be lambda. I can do, instead of a mass per volume or mass per anything, this is going to be a charge per length. I can also have a charge per volume when I have a volume, okay? So this is a charge. If you like, you can give it a subscript, but rho, you're going to see it in your book, is just rho. Yes, it's used for two different things. It's the same idea. You can have all kinds of densities. We're not going to be using this one for a little while. We're going to be using charge per volume as our rho because we're dealing with charges. But here, because we just have this ring, we're going to say charge per length. And the reason we use densities is that the density of a really huge object and a little tiny object are exactly the same, right? The density is the same. So my charge per length for this is going to be this lambda, charge per length, will be Q over the length of this. Well, that's half a circle, so that would be pi times A. Or I could say this charge is equal to dq over some little tiny arc length here. We'll call it ds. I know you're like, well, that didn't help much. I got a dq, but, and then I've got some other stuff, and you threw in some extra Greek letters. How does that help? Well, you may or may not remember from when we were doing angular stuff in Physics 1, we have the arc length S is equal to r theta. In other words, however far you are along a circle, right? If you have this is your theta, this is r, this is S. This arc length is r times theta. That should be somewhat familiar to you. So if we use this and write it like that, I could say lambda is equal to dq over r d theta. In place of my ds, I can rewrite it and say dq after all of this is equal to lambda. That's a density, so it's a constant, times r d theta. Now, hopefully you like that a little better. In fact, it's not r in this case. The radius is actually an a, right? Because that's the radius of this circle. So I plug this in here. This is really the trickiest part of doing this problem, believe it or not, even though I've got an integral in here. This is now equal to k over a squared integral sine of theta. I'm going to put all this stuff in here. I'm going to say times lambda a d theta. And lambda and a are constants, so we can pull those out. So that's really nice. Okay. And then I just have sine of theta d theta going from 0 to 180 degrees. Okay, so the integral of sine theta d theta, so this becomes, this is ey. I'm going to move over here. Rewriting this, I'm going to have a k over a squared lambda times a. Integral of sine theta is cosine theta. I think there's a minus sign there. And I'm going to evaluate it from 180 degrees, or pi, to 0 degrees. And so this cancels with one of the a's, and this becomes k over a lambda cosine of 180 degrees. So I've got minus cosine of 180 degrees minus a negative cosine of 0 degrees. Cosine of 180 is negative 1, so a negative of a negative 1. This whole thing right here just gives me a 1, and then this is a 1 right here. So 2 negatives make a positive, so I get a 2 out of this. So all of this together gives me 2k over a, and then I can substitute in lambda. I can use this expression here, q over pi a. Where this is just 2k, 2q over pi a squared. And that's my electric field in the y direction. That's how big this is. So if I know my value of q, I can put it in. I've got k. If I know my value of a, then I can actually get my electric field. The point of this is to, one, show you how you're going to use your calculus. And the trick is really using these densities, okay? Because I've got two expressions for the density. It's a constant value, this lambda, charge per length, and I can write it either in the total charge over the total length or the little tiny dq over ds. And then I just do algebra and a little bit of calculus along the way. Now for completeness, I will tell you we also have a surface density, and this is charge per surface is rho. So you're going to see that as well. These are your three charge densities, whether you're doing a charge per length, if you have like a long rod or a curve. This is going to be charge for surface, like a plate. Charge per volume might be if you have a sphere or some big chunk of material. It turns out that doing these kinds of integrals is not easy to do. Big surprise. This is a fairly straightforward one to do. The integral isn't too bad, but you can easily write situations where the only way you can do this integral is to numerically evaluate it. To have a computer set up and add up all the little tiny pieces and add up all the vectors to do that piece, because it's just not set up in a way where you get a nice equation like this.